Hi there, folks. Today we are going to be covering Chapter 7, Sections 1 through 3. We've now completed the core of what is traditionally taught in a Calculus 1 course and a little bit of what's taught in a Calculus 2 course, though we did go at a much more accelerated pace than a traditional calculus course because we're BioCalculus, and so we go at a quicker pace, but we cut some of the material out. Today, we're going to be covering an introduction to differential equations. Now, differential equations is a course in and of itself. Math 420 at American River College is differential equations, and it's a very, very heavy course. Lots of integration, lots of abstract concepts, but it introduces you into how to actually solve differential equations, equations which have derivatives in them. And it can be very, very difficult. There's a lot of different techniques. When you think about the integration techniques that we had, that's just the tip of the iceberg when it comes to solving differential equations. Today, we're going to focus more on the theory side of things. We're going to be talking a little bit about modeling with differential equations. We're also going to be talking about phases, plots, equilibria, and stability, which is really an introduction to the idea of chaos theory. And then we're also going to be doing direction fields and something called Euler's method. Euler's method, it's very, very tedious. And honestly, the best approach that we will have will be to use an Excel spreadsheet to do it. And I'll show you the basics of how to do that. But we're mostly going to be just introducing this idea. Today, we're mostly going to do one-dimensional stuff, though. And what I mean by one-dimensional is we're going to be talking about a single population. When we're talking about differential equations, we've already talked about this previously, but a differential equation is what's used to model just about everything in the universe. It's when you start to relate rates of change to initial populations. And so if we are thinking about the population of bunny rabbits, for instance, we know that the rate of change is going to be proportional to the population. We could do that for other populations too, but we can also start saying what happens when they interact. When we start talking about how different populations interact, that would mean that we would be talking about two or more populations, and so we'd be dealing with two or higher dimensions. For one-dimensional stuff, we'll be talking about a single population. And that kind of leads us to our introduction. And so what is a differential equation? And this is kind of what we were just talking about, which is kind of interesting. Often in modeling, you find that the rate of change of something is dependent on a number of factors, including how much of the something we have. Take, for instance, population. Suppose you have cells, which split every 24 hours. Then that means the rate of change of the number of cells is proportional to the number of cells that you have. This gives us the following differential equation, dy dt equals ky. This k is representing the constant of proportionality. Suppose that k were equal to 1, can you think of a function which is equal to its own derivative? Well, when we think about functions which are its own derivative, the main one that should come to mind is the function e to the t, with it being t because we're talking about dy dt. And so e to the t would be a solution of this differential equation if k were equal to 1. Now, solving differential equations like that can be tricky because when you look at this differential equation, you might not initially be seeing that there's an e to the t function in there. And so in our next lesson, we'll talk about some techniques for solving these things. For now, we just want to get the big picture. Here's another example, which is a little bit more interesting. And so suppose that you have a standard room and let u be a function of 4 variables, x, y, z, and t. And we'll let this represent the temperature at each point, x, y, z, in the room at time t. It turns out that the rate of change of temperature is always going to follow this differential equation. This differential equation is called the heat equation. It's also known as the diffusion equation. Basically, the rate of change of this temperature function with respect to T is proportional to the sum of the second derivatives with respect to space. And this is a law of nature. This is how we can actually model temperature and how temperature changes within a room. This also works with how smells would diffuse or how anything diffuses. If we're talking about population of cane toads in Australia will be diffusing at a similar rate. It'll be spreading at a rate which is following this differential equation. And so these two things are called differential equations. The problem, or the population one, this first one, is considered an ordinary differential equation, while this one is considered a partial differential equation. The key difference is when we look at this one up here, we're only talking about a function of a single variable. While down here, we're talking about a function of multiple variables. Now, we're not going to spend much time going into functions of multiple variables in this course. If you take Math 356, you will be dealing with functions of multiple variables, including space and time and multiple populations and all sorts of different things. But for our purposes, we're mostly going to be focusing on the ordinary case. Everything around us is defined by them. Yeah, and so we can model everything in the universe using these differential equations. Sometimes ordinary, sometimes partial, but just about everything is modeled by them. Now, we have ways of classifying them, and this is where we're going to get a number of key terms. And so the order of a differential equation is the order of the highest derivative appearing in the equation. And so when we look at this equation here, y double prime plus 2y prime plus t cubed, we would consider this a second order differential equation because there's a y double prime in there. If we had a y triple prime, meaning we were talking about a third derivative, we would say that it is a third order differential equation. The next is an initial condition. And so an initial condition is a starting value, which you can use to find a particular solution of a differential equation. When you think about a differential equation, even just this one here, the y double prime plus 2y prime equals t cubed, this is actually going to be defining a set of equation or a set of solution curves, which will satisfy this equation. Much like when we were doing integration and we got that plus c term, well, here we're going to see a ton of plus c terms pop up. But if we have an initial condition, like we know what the initial temperature is, or we know what the initial population is, often we can find a particular solution for it. Instead of having the plus c term, meaning there's an infinite number of solutions. If you are given that initial condition, that initial population or something, we call that an initial condition. The next one is an initial value problem. And so an initial value problem would be something like this. Y prime plus 2y equals t cubed, where y of 2 is equal to 1/4. And so when you evaluate the y function at time 2, we get 1/4 out of it. And so this would be considered a first order initial value problem because it's first order from the single derivative. And then this is an initial value problem because we have an initial condition attached to the differential equation. We then have three main classifications for the types of differential equations that we're dealing with. The first is pure time differential equation, and we've actually already done a pure time differential equation. Pure time differential equations are differential equations which only have t variables in them. And so they're not tied to the initial population, to whatever your population is. And so, for example, y prime equals 3te to the t squared would be considered a first order pure time differential equation. And what makes it pure time is over on this right side, we don't have any y terms. There are no y terms in here except for y prime, which is the derivative of y. If there were a y term floating around anywhere in here, other than the derivative of y, then it would not be considered a pure time differential equation. An autonomous differential equation is the exact opposite. And so an autonomous differential equation is a differential equation which is only tied to whatever your derivative variable is. And so, for example, y prime equals y cubed plus 2y would be a first order autonomous differential equation. And it's autonomous because there are no t's in here. If you saw the independent variable floating around in here, then it would not be autonomous. And that's the third case. The third case is non-autonomous differential equation. A non-autonomous differential equation is a differential equation which has both t and y values. And so this example here, y prime plus 2y equals t cubed, this is a first order non-autonomous differential equation because we have the derivative of y, but we also have a y term and a t term. And as soon as we see that we have both a y term and a t term, that tells us that it is non-autonomous. When we think about the difficulty of solving these, pure time differential equations are typically the easiest to solve. Autonomous differential equations, they're usually not too terrible to solve, but it really depends on how bad the functions are. And non-autonomous differential equations can become very, very difficult to solve. Yeah, I even wrote in here, there are many, many methods to solve these things. And if you're interested in learning all of them, you'll be taking differential equations courses. And so here's a sample problem, which is just kind of introducing the idea of this. And so this is called the Weibull equation for the dynamics of a drug concentration. And so it's given by dc dt equals k over t to the b times c sub s minus c, where k, c sub s, and b are all positive constants and b is less than or equal to 1, or sorry, just less than 1. Notice that this differential equation is undefined when t is equal to 0. And so this is saying that it's happening after an initial time. The first thing says, state the order of this differential equation. Well, looking at this, there is a derivative term in here. It is a first derivative, which tells us that this is a first order differential equation. Is this differential equation pure time, autonomous, or non-autonomous? Well, looking at this, our dependent variable is c and our independent variable is t. And this rate of change has a t term and it also has a c term. Because this rate of change is related to both time and the population itself, we would say that this is non-autonomous because it's related to both of them. C is a trickier one. State in words what this differential equation says about how drug dissolution occurs. And this is something that takes some practice to really understand what these equations are telling us. Looking at this dc dt term is representing the rate of change of the concentration with respect to time. This k term is being multiplied by all of the rest of this. And so in this case, it's being divided by t to the b, which would be corresponding to being inversely proportional, whereas c sub s minus c, it would be proportional to that. C sub s is going to be some value which could be the supremum of it. That would be my guess. But it's some carrying capacity that we have. It's some value which is above our C value in general. Or it could be the ending concentration. Perhaps it's the standard concentration. That might make more sense for it to be the standard concentration. So this is the amount that it'll hopefully approach with respect to time. And so to state in words what this differential equation says about how drug dissolution occurs, I would say that the rate of change of the concentration of the drug in the system with respect to time is proportional to the difference between the standard concentration and the concentration at a particular time, and inversely proportional to time taken to some exponent, where that exponent is less than 1. And so that's how I would state it, just dealing with the idea of proportionality. And so it's proportional to this and it's inversely proportional to this term. And then just recognizing what these terms represent. The last one, it's mostly just an algebra exercise. And so verify that C is equal to C sub S times 1 minus e to the negative alpha t to the 1 minus b is a solution for this system where alpha is equal to k over 1 minus b. In order to do this, you just have to take this formula, plug it in for C, and then you have to take your dc dt, so take the derivative of this with respect to t, and then verify that the two sides are equal. If you wanted to go with the trigonometry proofs, you could take the derivative of dc dt, so take the derivative of this function, and then just show that it's equal to the right side. And that's all that it's asking you to do. So that's the terminology. What might be more interesting is to actually see the visual for these differential equations. And to see the visual, what we need is a direction field. And that's what this graph here is. So suppose that we have some ordinary differential equation, which is of the form dy dt equals f of t comma y. So some function of both time and space, where f could be a function of y, t, or both. Then the function f of t comma y tells you what your slope is at every point, because this is saying the rate of change. And remember, rate of change is just slope. And so the slope is equal to whatever this function is telling you. A graph which shows the slope at every point is called a direction field, or a slope field, or sometimes a phase portrait, or a phase diagram, or a vector field. These terms can be used interchangeably at this point. As we get to more and more intricate things, you'll see phase portraits are typically representing two-dimensional things. Vector fields can be used for a wider variety of objects, though. And the graph of a particular solution, which follows through your graph, or through your direction field, is called a solution curve. And here I have an example of one. This is one for dy dt equals y squared minus t squared. And let's actually see if we can figure out how to graph something like this. And so we're going to start by doing it by hand, because we got to try it by hand first, right? Dy dt equals y squared minus t squared. And I will show you how tedious these things can get. And so to draw a direction field for this, what we're going to need is we're going to need a Cartesian coordinate system. And we're not going to go too detailed with this. Let's just go out to 3 in all directions, because that will be more than enough. 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Now, what we're going to do is we're going to basically be creating a series of points, and we're going to be determining what the slope is at each of those points. And in this case, we're going to have 49 different locations which we're going to be examining. And you can already see my graph is not exactly to scale, but that is okay, because we are just going to show roughly what these things look like. Oh, very not to scale, very not to scale. And there we go. What we are going to do is we are going to use this equation to calculate the slope at every single point on this graph, including on the Cartesian coordinates, including on the axes. And really the only way to do that is to start plugging in values. And so let's just do a couple of points so that you can see what we're talking about. And so let's suppose that we are at the point 2, 1. Well, at the point 2, 1, that would be this point right here, right? Well, at 2, 1, we're going to get that dy dt is equal to, remember this is t, y. And so it would be y squared, which is 1 squared, minus t squared, so minus 2 squared. 1 minus 4 gives -3. So at this point, we know we are going to have a slope of -3. Now you could go down 1, 2, 3, and over 1, and then just have a large arrow going down that way. Typically, we won't do that because that's just going to be a very long line, and the entire graph would then become extremely long lines. And so instead, usually what we do is we try and just make it so that it's going in the direction there, but we try and make it so that it has a length of around 1. Sometimes you'll go with smaller arrows, sometimes you'll go with longer arrows, but this is generally how we would go about it. And I usually start at that point, and then I just create an arrow going in that direction. Some people prefer to have it centered on the point, and you can do that if you like. But this is how I'll typically be doing it. I'll just be going from that point, so I know at that point, I'm going in that direction. Let's do another point. How about at -1, -1? Well, at -1, -1, we get y prime is equal to -1 squared minus -1 squared. So -1 squared minus -1 squared is 0. And so that tells us that at -1, -1, we're going to be going at a slope of 0. And so we're going to be just going flat because this is what a slope of 0 looks like. Let's do another point. How about at the point -1, 3? At -1, 3, well, now our y prime is going to be equal to, what would that be? That would be 3 squared minus -1 squared, which is now 8. So it's going to be going extremely fast in the upward direction. Now we just have to do this with every single point on this graph. And it's tedious. It's very, very tedious. But we can use some symmetry arguments to get it done fairly quickly, depending on how you define fairly quickly. And so where I would start was I noticed that this one was 0. Identifying where it's going to be 0, well, if y is equal to t, or if y is equal to -t, we're going to be getting that slope of 0, which tells us that on the main diagonal, we get a 0. Also, if we're along the line y equals -x, we're going to get 0. Now we can try and figure out some of the other values. Let's maybe start with the axes, because the axes should be pretty easy. If we are at this point here, this would be when y is equal to 0. And when y is equal to 0, we're just going to have -t squared. And so -1 squared is going to be -1. At this point, it would be a -2 squared, which would be -4. And so it needs to be a little bit steeper than that. This is where we're going to kind of be eyeballing it. At this one, it would be -9. And notice that if we're going in the negative direction back here, it's going to be the exact same. And so at this point, it's going to be -1. At this point, it's going to be -4. And then at this point, it's going to be -9. Yeah, that one might not be quite that steep. Again, we're just looking for rough directions. We can then do the y-axis, because the y-axis, well, very similar, but now the t value is 0. When the t value is 0, we're going to get 1, we're going to get 4, we're going to get 9, we're going to get 1, we're going to get 4, we're going to get 9. Now we just have all of the other spots. And so looking at this one, at this point, we ended up saying that it was a slope of -3. Using the symmetry argument, we know that this over here is going to be at -3. So it'll be like right there. And we'll also have it reflected down this direction at -3 and a -3. At this point, we are at 3 and 1. And so that is going to give us a -8. So a -8 and a -8 and a -8. At this point, it's going to be a -5. And so again, it's going to be pretty steep. Not as steep as these towards the center, but still very steep. And all of those values, the 8, the 5, the 3, they're actually going to be repeated over in these other sections, but now they're going to be positive. And you can actually calculate them all out. And so here we had the 8, which again is very steep. This one, it's going to be 4 minus 1. And so that's going to be a 3, which is still pretty steep. And then at these, we should be at 5, which again, very steep. And so we now have this graph, and it might not be very clear because it's a bunch of arrows, but we can start to see what the behavior is for this phase diagram or this direction field. And so with this direction field, we can see what curves are actually going to be doing. And we can just choose any starting point we want and just kind of follow the curve and see what happens to it. And so, for instance, if we started at a point up here, well, up here, we can see that it's just coming off of something that was flat, and then it's going to be going in an upward direction. And it's going to get steeper and steeper and steeper, it looks like. The question might be, though, what led to that point? And if we look behind or before this point, we can see that it was coming in a downward direction. So we would have something coming in a downward direction to hit that point, level out, and then go in an upward direction. We could try another point. Let's say that we are down in this area here. Well, looking down here, it's going to be coming in a downward direction, fairly steep. But as soon as it crosses this line of y equals x, we know that it's going to go flat. And as soon as it goes flat, it's going to start to go in an upward direction, because in this entire region down here, it's going in an upward direction. But as soon as it hits this line, the y equals -x line, it's going to flatten out again. And after it flattens out, well, the arrows are now pointed in a downward direction. So we're going to get something which is looking like this. We could then ask what led to this point. And well, we can see that everything's coming in a downward direction from that. So we get a curve like this. And we can just carry on doing these types of drawings to try and figure out what the curves look like. And so a point over here, for instance, it's going to be coming from flat, and then it's going to go in a downward direction. This point would have been coming from something which was going in an upward direction. Then it would have crossed some point here, and we'd get a curve something like this. And we can create as many of these curves as we like. What this is doing is this is telling us what the behavior of this differential equation actually is. And we can see that things are starting in a downward direction. Then it looks like there's a little bit of a lift, and then eventually it starts to go back down again. For some of these, it starts in the negative, and if it starts negative, it doesn't seem to ever want to go positive again. And we can see that this will then come up and up and up, and it will eventually cross and go down, and then same here. And so this is the general behavior of this differential equation. We might do, let's say, one more, something coming down here, crossing, going up, and going down. And often it's good to draw an arrow going to the right to show that all of these are going in the right direction. In this case, we're dealing with time, and time only moves in one direction. Later on, when we're dealing with higher dimensional things, we might see different behavior. And now comparing this to the graph that we had, share screen, they look fairly similar, which is good. This is the computer generated version, and when you compare that to the one that we created, the behavior is looking fairly similar. Like I note here, the graphs can be very tedious and time consuming to create, which is why we have some resources to help. Personally, this is my favorite resource, dfield. It is a Java tool which is great at creating these direction fields. And if you'd like, you can download it for free. It looks like it's from University of New Mexico these days. Is that what CSUNM is? Could be wrong there. It used to be through Rice University, but it seems that the individual who was working there has since moved to a different institution. But dfield is the program which I use for one-dimensional direction fields. P-plane is one we will talk about probably next time. And that's one which is good for two-dimensional phase portraits. And so if you download this, I already have it up and running. Let's see if I can get it on the screen. And we'll talk about that stuff later. Here we go. And so this is dfield. If we want to plug in the graph that we just did, we would say that we are dealing with the function y prime. Y prime we set equal to y squared minus t squared. We're not using any parameters, and so we don't have to worry about that. The independent variable is t, and the graph that we did was from -3 to +3 in the t direction, and -3 to +3 in the y direction. And this is what the graph looks like. Let's see if I can move this down here. There we go. Oh, I can't move that on the screen though. Sorry about that. And so this is what the direction field looks like. And note that it's doing arrows. It's got a lot of arrows in there, more than we did, certainly. What's special about this though, is you can then click anywhere on the graph and it'll actually show you what the particular solution is. And so again, when we talk about particular solutions, this graph with all of the arrows is showing what all of the different solutions to this differential equation are. If we have an initial condition, an initial starting point, like let's say that we know that at time t equals 0, we know that there is a value of 1.5. Well, that would give us this curve right here. If we knew that at time t equals 0, the population was -2, well, we would get this curve here. And depending on what our initial condition is, what we know initially, we get a variety of different curves. And what I'm clicking here is all of the different possible initial conditions. And this is showing all of the different things that can happen with this differential equation, all of the different solutions. There's an infinite number of solutions, but they're all going to be following these particular shapes. And so we can then ask questions like, what is the long-term behavior of these differential equations? And well, looking at this, it looks like we might have some which are going off to infinity, but a large majority of them are going in a downward direction. Some of them will begin in the negative and will continue to increase and then go down towards negative infinity, following some line which appears to be similar to y equals x almost. Might not be exactly y equals x, but it's similar to it. And some are going to be increasing before they start to decrease in the positive direction. This is what the graph of this differential equation looks like. Depending on the differential equation, you are going to get a wide variety of different outcomes. And so let's throw another differential equation in here. This will work no matter what the function is that we're dealing with. What would happen if we were dealing with a y squared, or let's say y cubed minus y plus t cubed minus t. Let's even make it a plus t just to make it a little bit more interesting. I have no idea what this graph's going to look like. Looks kind of interesting. Has a fairly similar behavior to the last one, but we can see that it starts to increase at this point. And so this again is a non-autonomous differential equation because it's dealing with both y and t. What happens if we do a pure time differential equation? So pure time differential equation would be something like t cubed minus t squared. Well, notice all of these curves are the exact same curve. They're just escalated a certain fixed amount. What that corresponds to is an integration when you're doing your plus c. The plus c is telling you what value you're starting at. And so all of these curves are the exact same curves. And we could actually integrate this to figure out what it is. Looking at this, it would be a 1/4 t to the fourth minus a 1/3 t cubed. And so that would give us this graph right here. If you wanted one which was easier, we could do something like just y equals t. We know that when we integrate t, or let's make it 2t, just to make it even nicer. We know when we integrate 2t, we get parabolas. And so in theory, when we graph this phase plane, we should get the standard parabola. And sure enough, we get the standard parabola. We could do this for other functions. If we integrated 1/t, we know we get logarithms. And when we graph this, sure enough, these curves are logarithms. Over on the other side, on the negative direction, we're still getting logarithms, but these would be the natural log of negative t. Remember that when you integrate 1/t, you get an absolute value that comes in there. And this is giving us the ability to do the negative values as well. What if we did a sine? Well, hopefully we're getting a negative cosine. And sure enough, if this is our 0 value, this would be corresponding to the peak or the valley, and that would give us the negative cosine value. And so that's what happens when we do pure time. We get all of these curves are the exact same curve, they're just shifted up and down. What's more interesting is when we talk about autonomous differential equations. So remember, those are equations which are tied solely to the variable y, or whatever our starting variable is, whatever our population variable is. And so let's consider something like y equals, how about y squared, or yeah, let's do y squared minus y. That should be an interesting one. And I'm going to change the t value so that it goes out to t equals 10, just for good measure. There we go. And so notice with this one, we now have something which, instead of being the same as we're going up and down, this is the same as we go across. All of these arrows are the exact same because it doesn't matter what time we're talking about. This is always going to give us the same differential equation. It's tied strictly to the population of y. What's fun about this is we actually get some fixed values. And these fixed values are things which we're going to be approaching with, or as time goes on, or going away from as time goes on. So this is what the curves look like. Looking at this, if we start out above 1, we're going to be going off to infinity. And it looks like it's going to be following an exponential curve. If we're between 0 and 1, everything is going to be going in a downward direction, and it looks like it's going to be approaching 0. If we look at everything below 0, everything is going to be increasing up towards 0. This is the standard behavior for an autonomous differential equation, where you're going to have fixed values that it's going to be going towards or going away from. And we call these equilibrium values. I believe that's the next page, but let's take a look. Oh, it absolutely is. How about that? And so our next topic is equilibrium. And in particular, equilibrium when we're talking about autonomous differential equations. And so as mentioned, an autonomous differential equation is a differential equation which is tied solely to the function y. Y squared minus y, is that the exact function that I was dealing with? I think it might be. That's kind of nice. And so when we have a autonomous differential equation, equilibria occurs when we have that f of y is equal to 0. Because if f of y, if this function is equal to 0, that means the rate of change is equal to 0, which means it's flat. But it's going to be flat forever, which means that it's always going to be staying in a flat direction there. And we can consider this one, dy dt equals y squared minus y. What are the equilibrium values of this ODE? Well, if we set this equal to 0, we're going to get at 0 and at 1. We're going to be having a equilibrium, because at 0 and 1, y squared minus y is equal to 0. Now, what's interesting is depending on your initial values, you will typically either approach or go away from these equilibrium values. And the example that we had up on the screen, this one right here, y squared minus y, what are the odds? Notice that for the top values, it's going away from 1. In the middle, it's also going away from 1. But on both sides of the 0, it's approaching the 0. This allows us to determine the stability of these. And so in this case, we would say that at the value 1, this is unstable because everything is going away from 1. Nothing is going to go towards 1. Everything is always going to be going away from the 1 value. The 0 value, we would consider a stable equilibrium, because if you're a little bit above it or below it, everything is going to be approaching that 0 value as time goes on. When things approach it, it's stable. When things go away from it, it's unstable. There is a third situation called semi-stable. And semi-stable is where you're approaching on one side, but you're going away on the other side. Simple example of that would be y prime equals y squared. When we look at this one, from below, everything is approaching 0. From above, everything is going away. And so 0, we would consider an unstable equilibrium, or sorry, a semi-stable equilibrium. They don't happen as often, but they do happen. And so keep that in mind. To the right is the diagram of the above ODE, and we already saw that one. And these things are fairly easy to construct. And so let's actually draw some of these. I have a few guidelines for how to draw them, and I have a few practice problems, but let's do a different practice problem instead. And so let's stop the share. There we go. And let's do this one. I want to do P prime. So our population is P. And let's make this equal to P to the 4th. Then I'll make it minus P to the 3rd. And then let's make this a minus 6 P squared. And so again, this is an autonomous differential equation. So we're going to need to be able to graph this. But before we can do that, we need to figure out where our equilibrium values are. And so first thing we need to do, let's find our equilibrium. To find our equilibrium, we need to take this and set it equal to 0. So p to the fourth minus p cubed minus 6p squared equals 0. Now this one is fairly painless to solve because we can factor. And when we factor this, we're going to get a p squared times p minus 3 times p plus 2 equals 0. -3 and 2 should give the -6, and the cross term should cancel. And so this is going to be the factored form of this left side. Now we set each one of these equal to 0. The p squared being equal to 0 is going to tell us that p is equal to 0. The second one is going to be at p equals 3. And the third one is going to be at p equals -2. These are our 3 equilibrium values. And so when we go to graph these things, we can create a quick graph. And we won't even put all of the different values on our chart because we know that the time doesn't really matter. And really what we're interested in is these 3 particular values. And so on our graph, let's put those 3 values. And so we'll have p equals 0, which would be just coming straight along here, where this is p and this is t. P equals 3, we'll just pop that up here. And then the other one is p equals -2. We'll put that one here. So now in order to determine whether or not they are stable, unstable, or semi-stable, what we'll do is we'll choose test points from the 4 regions, because there's 4 regions here that we've broken this up into. And so we just have to determine if it's positive or negative on each one of those regions. And if it helps, we can use this formula that we got, the factored form of it, where we said p prime is equal to p squared times p minus 3 times p plus 2. We know the general shape of these curves. It's always going to be exponential or hyperbolic tangent. Hyperbolic tangent meaning it goes from one curve to the other curve and it kind of follows an exponential path. We just need to determine, is this going to be positive or negative in each one of these regions? And so let's start with the top region. If we did a test point at, let's say, p equals 7 or 10, doesn't matter, anything greater than 3. Well, at 10, we know p squared is positive, p minus 3 is positive, and p plus 2 is also positive. And so that tells us on this region, everything is going to be positive. What that tells us is that we're going to have slopes, if we were to draw all of those arrows, that are going to be going in the positive direction. Well, if we wanted to do the particular solutions, that would tell us that we are going to have curves which are going to be following exponential curves. Choosing a value between 0 and 3, let's say 2. And so at 2, p squared is still positive, p minus 3 is now negative, p plus 2 is going to be positive. And so positive times a negative times a positive, we're getting a negative on this region. We could draw the arrows again if we wanted to, but we know that the curves are going to be going from this equilibrium down to this equilibrium. And it'll be approaching it with the limit. And so it'll be coming from here, going down, and then it'll just follow that curve. And so this is what these curves are looking like. Choosing a value between 0 and -2, how about -1? Well, at -1, we get that this is positive, this is negative, and this is still positive. And so that means we're still going to have a negative, which means our curves are still going to be following that same general shape, going in a downward direction on that interval. And then the last one, when p is equal to -2, well, when p is equal to -2, or sorry, when p is less than -2, so let's say at -10, this stays positive, this is negative, now this is negative, which means that we're going to end up with a positive, because positive times a negative is a positive. Well, that tells us we're going to get curves which are going in an upward direction. And since we know it's exponential, they have to look something like this. This is what the phase diagram would look like for this. And this is showing not all of the arrows, but it's showing all of the particular solutions of this, as well as what all of the equilibrium are. And now that we have the phase diagram, we can classify these very quickly. And so p equals 0, well, it's going from down, so it's going away from it on the bottom and it's going towards it on the top. That tells us that this one is semi-stable. At p equals 3, it's going away from it on the top and it's going away from it on the bottom. That tells us that this is unstable. And at p equals -2, curves are going towards it on the top and curves are going towards it on the bottom. That tells us that it is a stable equilibrium. And that's how we can solve these types of problems. And so we were given this problem. We weren't asked to find the general solution for it because that's much harder. What we will typically be asked instead is to provide the phase diagram for it and find and classify the equilibrium. And here we found and classified the equilibrium, and we used the phase diagram in order to do it. We can check our answer if we want to using D field. And so let's pull D field up. Here we go. And so our differential equation was P prime equals, and then it was P to the fourth minus P to the third minus 6P squared. Let's change our maximum and minimum P values to go from -5 to +5. And here we can start to see the graphs of these. It's a little harder to see because of how compressed it is. So let's change the T values to go from -3 to +3 again. Let's graph that. And even then, it's still a little difficult to see the exponential curves in here. But we can see our equilibrium values. And so at 3, we can see that it's flat. At 0, we can see that it's flat. And at 2, we can see that it's flat. That's what makes them equilibrium values. If we started at 3, we'd be at 3 forever. If we're a little bit above or below 3, though, we can see that it's going away from it. And so it's curving away. It's curving away above, it's curving away on the bottom. So this is curving away from the 3, which tells us that it is unstable. At 0, it's going towards it on one side, and it's going away from it on the other side. That makes it semi-stable. And then the other one at -2, it's coming towards it on the top and it's coming towards it on the bottom. That makes it stable. And so those are our 3 different classifications of these. Hopefully that helps. We can do this with any function. The ones that I put in the notes, they're a little bit simplistic. And so typically I like to give ones which are a little bit more complicated, ideally one that has all 3 of the different classifications. but we can get a number of different types of this, or different differential equations. We can get them that have 20 different solutions or 20 different equilibrium values. We can get them where there's a single equilibrium value. One which has a single equilibrium value, for instance, we could do p minus 2. We did p minus 2, well, there's a single equilibrium value, and that's going to be at positive 2. We made it a negative p minus 2, or negative p plus 2, let's say. We still have that single equilibrium at 2. And notice that the difference is now it's stable, whereas before it was unstable. If we wanted more, really the higher the exponents, the more solutions you're going to get. And so we could make this so that it was a p minus 2 times p minus 3 times p plus 4, or let's even make it so it's a little bit nicer. How about a p minus 4, a p plus 4, a p plus 2, and then we'll throw in a p squared just for good measure. If we multiplied all of these out, we would end up getting a p to the 6th term. And this should have 5 equilibrium points looking at it, because when we set each one of these things in parentheses equal to 0, we get a 0. And so let's graph this one. Let's go negative 6 to positive 6. And notice this is what our graph starts to look like. At the top and bottom, it's trickier to see because of just how fast it's going. Let's stop. It's having difficulty calculating because the computations get so big so quickly. But we can see when we zoom in a bit on this, maybe let's go from 0 to 3, that we have things which are increasing on this interval and decreasing on this interval and increasing on this interval. And so we're going to be getting these same types of curves. Looking at this, we would say the 4 value is unstable. The 2 value should be stable because everything's going towards it. The 0 is semi-stable because it's going towards it on one side and away from it on the other. The negative 2 value is unstable because it's going away from it on one side and away from it on one side and away from it on the other side. And the negative 4 value is stable because it's going towards it on one side and towards it on the other side. Because of how large the exponents are on this, it goes very, very fast. Let's even make it so this is like a 1/10 and see if that improves. That improves the curves a little bit. Maybe 1/50th. Yeah, now we can start to see behavior a little bit nicer, where it starts to go from the 4 and then it goes down to the 2, or it goes from the 0 up to the 2. But it's doing some heavy lifting because these computations are getting a little bit messy when you have exponents quite that large. And so that's the idea behind graphing these phase diagrams and classifying the equilibrium values. If you want, here are the steps you can follow. Here are some additional practice problems. And then there's also a note in here that the homework in the textbook gives a different way for determining equilibrium values, which you can use if you would like. The way that it would do it is it basically graphs the function without actually solving what the phase diagram looks like. And so let me show you what it would do. For the example that we had on our whiteboard, it is p prime equals p to the 4th minus p cubed minus 6p squared. The way that your textbook would approach this is it would actually graph that function. And so it would say, what is the graph of y equals t to the 4th minus t to the 3rd minus 6t squared look like? Well, this graph, this equation, is representing the rate of change at a particular time. And so here we would have a positive rate of change. Here we would have a negative rate of change. Here we would have a negative rate of change, all the way around here, negative rate of change. And then here we would have a positive rate of change. Well, if we have a positive rate of change before the -2 and a negative rate of change after the -2, that would mean that values would be coming towards this -2. And so -2 would be a stable equilibrium value. At 0, we can see that we have a negative before it and a negative after it. That means that values are going to be going away from the 0 and towards the -2, or on the right, they would be coming towards the 0. And so I would make this 0 a semi-stable equilibrium. And then at this last one, the 3 value, well, we have a negative rate of change before it, which means it's going away from the 3. We have a positive rate of change after it, which means it's going away from the 3. And so we would have an unstable equilibrium at 3. Personally, I don't like this approach because this graph, it's not actually representing the curves that we would see. The curves that we would see and the curves we saw in D field and the curves we saw on our whiteboard are the actual solutions to our differential equation. This curve does not represent the actual solution to the differential equation. And so while it might help to quickly determine when equilibriums are stable, unstable, or semi-stable, it really loses sight of what this is actually representing. This is representing differential flows. And when I say differential flows, what I mean is this is how things are moving and changing. If we think about how a cell population grows or changes, it'll be approaching one of these fixed values. And let me stop the share and show you some of the bigger picture ideas here. And so when we look at this one, oh, this is one example, but let's create a different phase diagram, different autonomous phase diagram. And for this phase diagram, let's make it so that it looks something like this. And we will say that, I'll even get rid of the negatives because we won't care about the negatives. Let's have an equilibrium value here. Let's have an equilibrium value here. And then we will have no equilibrium value above it. Let's say that our diagram is showing curves like this. And then in this interval, we will be having something similar. And then let's say that above that, it's going even more. And let's say that this is a population of cells. And so this is a population P with respect to time T. And we can be as specific as we want with what type of cells we're talking about. Let's say that we are talking about the cells in your 4th toe on your left side. And this is the number of cells that you should have according to your biology and the differential equations which govern your body. This right here, well, you start with 0 cells in your big toe, hopefully, because before you're born, you don't really have those toes at some point, at least. And so we know that we should be approaching this value, and this would be the number of cells which you should have in your toe. Well, what happens if something goes wrong? And so somehow you're exposed to something or something happens and you end up being pushed above that number. Well, if you get above this threshold, what might happen, and who knows what the cause of that is that you'll then be placed into this new growth cycle. And where you see this new growth cycle, you'll now see that it's approaching some new level set. What this is just described is what a non-malignant tumor would look like. And so a non-malignant tumor, you have your standard number of cells, and then you have an additional growth of new cells, but it has a cap. And so the number of new cells are going to be capped at something. And the causes for that cap could be a number of things. It could be based on other populations, or there's a lot of different things. But we'll see that it'll then approach this new level. Well, what happens if it goes above that threshold there? Well, if it goes above this second threshold, now it's going to be seeing exponential growth. That's a malignant tumor. That's saying that we now have something which is going to be growing in an exponential way. And the only way that we can get it so that it is no longer growing in an exponential way would be to somehow get it down below these thresholds, or figure out what's causing it to go above those thresholds. And that's what the models for tumor growth are showing. If we have something where it's expanding in an uncontrollable way, that is a malignant tumor where the cells are just dividing like crazy. And we see this type of behavior in all sorts of biological processes. Again, these differential equations model anything that grows or changes, and the human body grows and changes. And so just about every biological process, there's some limit which it's supposed to be approaching. When something goes wrong, maybe it will no longer be going towards that. Or we'll have a disease where perhaps the amount of sugar which is going towards cells is regulated in a different way, in which case the equilibrium values that you should have are changing. And when things go really sideways, well, what happens when something like this happens? What if you do something to your body, or there's a disease in your body which causes one of these to flip? Well, now this is kind of nice because everything's going to be approaching this value, and maybe you want everything to be approaching that value. That might be a very ideal scenario. But if you overdo it, maybe you'll end up in this category, in which case you'll be seeing exponential growth, and that could be bad. Or maybe you'll see, for certain populations in the body, exponential decay above this set. And so if you're doing one behavior, you might end up in this equilibrium. And if you are at a different set, then your body might be pushing you towards this equilibrium. That's the type of thing where you can see this occurring with things like diabetes, where the amount of insulin that's being produced will be different based on how your body produces things. And as you age, these differential equations will also change with respect to time. And so as you're looking through different articles online and you start seeing differential equations pop up, you might start to ask questions like, what different characteristics will affect these differential equations? One of my favorite is when we start to analyze tumor growth and how chemotherapy works, because there it's very clear how chemotherapy is causing the death of immune cells as well as normal cells. And so, yeah, there's a lot of fun stuff that you can read once you start to understand how these things work. For now, though, again, we're just introducing the concept, and so I won't go into too much depth there. 356, you'll see a lot more depth. Oh, and congratulations, you just learned chaos theory. That's another big takeaway from this. The study of equilibrium is the study of chaos theory. Let's go back to this whiteboard. What chaos theory is the idea that a slight change in initial conditions can have a drastic change on end behavior. And so looking at this one, if we started out at this point right here, we know that we are going to be approaching this curve down here. And so this is what our end behavior is. If we start just a little bit above that, well, now our end behavior is going to be at this one. And so this slight change in initial conditions can have a drastically different end result. That's what chaos theory is. So congratulations. The last topic for today is one called Euler's method. And Euler's method is a tricky one. Conceptually, it's not that bad. But if you thought the graphs we were doing earlier were tedious, this is taking that up to the next level. In order to get good results for Euler's method, you have to do millions of computations. And I do not expect you to do millions of computations. And so in the homework, I made it so that you do not have to. But I would expect you to be able to use Excel in order to figure out 1,000 computations or something like that. And so suppose you can't solve a differential equation directly, but you want to know the general shape of the solution. Euler's method is a terrible way of accomplishing this. I love that I put that it's a terrible way. Good. It's a way of creating an approximation for a solution. That's really what it is. And it can help you determine long-term behavior, but it is not very accurate. There are other more accurate methods like Runge-Kutta, but even then you need to have much stronger computers than most of us probably have in order to come up with those approximations. Here's the general idea behind Euler's method, though. And so if you begin at a point, t naught, y naught, and you know what your slope is because you have some equation, and you know what interval length you would like to do, well, you can calculate where you would estimate the next point to be. And it's given by this formula, T1, I'll write it down real quick, Y1 is equal to T naught plus delta T time, plus delta T, comma, F of T naught, comma, Y naught, y naught plus that. Let me write that, y naught plus that. Plus f of t, comma, y, and it'll be t naught and y naught times delta t. What this is saying is, let's suppose that we have a graph, and let's suppose that we have a particular point on this graph. Well, let's use the blue pen here. And so let's say that this point here corresponds to our starting point, t naught, comma, y naught. Well, if we know what the slope is at this point, and so let's say that the slope is given by this direction right here. Well, we can then estimate where the next point is. And so our next point, we would expect to be somewhere along this slope. And so this point would be given by T1, comma, Y1. But how do we actually calculate what this new point is? Well, this new point would be given by taking our starting values and then whatever this change is here. And so this change from here to here is delta t, because it's a small change in the t direction. Well, then this change here, well, if we know what our rate of change is, we know what our y prime is, our dy dt, it'll be our rate of change times our delta t. But if our differential equation is given by dy dt equals some function of t and y, then this slope would be given by f of t naught, comma, y naught. And so that's how we get this point. This point is saying it's your starting point, t0, or your starting t value, plus whatever your delta t is. And then it's going to be your starting y value, y0, plus this term, dy dt times delta t. Well, dy dt, if it's given by this function, would be given by f of t naught, comma, y naught. And then we're multiplying it by delta t, the small change in t. That gets you your first spot. Well, now that you've got your next position, we would need to do this again. And so now the slope might be a little bit less, or maybe a little bit more. It really depends. Well, we'll go another delta t over, and we will calculate our next point doing the exact same process. And so this would then be t2, comma, y2. And then we could do it again. And we could do this as many times as we like. And that's really what Euler's method is. Euler's method is basically saying, instead of solving a differential equation, which we might not be able to do, we could just go one point at a time if we know the differential equation and figure out exactly where we expect that next point to be. It is extremely tedious because it's very difficult to get accurate solutions to these. And in the notes, I actually show that. And so let me do this real quick. And so here's the sample problem. Suppose that we have the differential equation dy dt equals y. And we know that our system has an initial condition of y of 0 equals 1. Note that the solution for this is going to be y equals e to the t, because y equals e to the t is its own derivative, and e to the 0 is equal to 1. And so e to the t is the solution for this. If we wanted to find what y of 10 is, we could break the interval 0 to 10 into intervals of length 1, and then use this Euler's method to approximate it. And so y of 0 we know is 1. Our slope at 1 would be 1. And then we could use that to calculate what y of 1 is. Excel is great at calculating these things. And I actually have a spreadsheet already prepared for this. And this one's dealing with y prime equals y. And so if this is our formula, and our starting t value is 0, and our starting y value is 1, we can set our delta t value to be 1. And this will show us what we would get after 10 units. Let's even make these wider so that we can see it a little easier. And so according to this, after 10 intervals, we would be getting 1024 as our y value. And let me show you how I calculated these. And so this value here, our starting t value is just coming straight from here. Our starting y value is coming straight from here. Our y prime is then equal to y, because that's the formula we have. Y prime is equal to y. For the next row, I said this is going to be equal to this term, E3, plus this value down here, our delta t value. Our next y value is going to be equal to our previous y value plus this value here times our delta t. And so it's going to be 1 plus 1 is 2. And then this is just going to be equal to this again, because that's our formula. I then just copied and pasted this all the way down. I made it so it went down to the first 1,000 terms. And that's what this repeated process would do. And so this is going to give us 1,024 is what we would expect to be 10 units later. Here's the challenge. We knew that this function was e to the t, and e to the 10 is nowhere near 1,024. And that's what this is showing. And so solving this, we get e to the t, and e to the 10 is roughly 22,000. Using 10 intervals, we got 1,024, which is nowhere near 22,000. If we had used 100 intervals, we would get 13,780. If we'd used 1,000 intervals, we would get 2959. And so 20 intervals would be saying delta x is equal to 0.01. In our spreadsheet, we can actually do that real quick. So 0.01, and I actually have this so that it'll go all of the way down to the 1,000th term, which would be 10. And I get 20,959. And looking at our thing here, 20,959. We're still off by more than 1,000. At 10,000 intervals, we're still 110 units away. Turns out that using a computer, you typically won't be able to get a sufficiently close approximation because, you know, Excel is only so powerful. And by the time you start hitting 1,000,000 intervals, the rounding error to your computations becomes just too great. And so you'll start to see some really weird behavior start to happen if you go too small. And even the approximations can get unwieldy. And so that becomes a problem. And if you need a better approximations, there are better approximations out there. But this is what Euler's method is all about. It's it's a way of approximating rates of change. And looking at this Excel spreadsheet that I made, you could make yourself, or you can make a better version of it. And we could use this to do any equations that we wanted. Let's do one that we started with. We started with y prime equals y squared. And then let's do minus y. And just to make it so I don't have to scroll down, I'll just make something that says end behavior. And I will make this be equal to this very bottom value, so that I don't have to scroll to see what it ends up with. And so looking at this, if we start at 0, 1, according to this, using delta t equals 0.01, we end up getting something. Oh, I know why, because I haven't actually changed the formula in here. And so I actually have to go and manually change this formula. I didn't make it so that it automatically does this formula. And so I'll say that this is equal to this value, the y value, squared minus this y value. And then I'll copy that, and I will paste it all the way down. And so copy and paste. And notice if we start with a y value of 1, it stays 1 all of the way down, which makes sense because 1 was one of our fixed points. And so we know that it's going to be staying at 1 the entire way through. What happens if instead of starting at a y value of 1, we start at a y value of 1.5? Oh, it becomes a number which it's unable to handle. My guess is because it becomes so large, so quick, that it is unable to handle that. Oh, and that seems right. It goes a lot quicker than I thought it would, but that makes me wonder if maybe I did my calculations wrong here, but I don't think I did. Let's see. This is times G3. That looks reasonable. Yeah, well, that seems reasonable. And so it becomes very, very large, very, very fast. I didn't expect it to go that large that fast, though. According to this, it's saying that by the time we are at 1.22, it's already an unreasonable number. And that does seem alarmingly fast. But it does make sense that it would go off to infinity because that one value we found to be unstable, I hope. Let's actually pull up this real quick, y squared minus y, and verify that it was unstable. Otherwise, my Excel spreadsheet might be off. And so we will say y, and then we will say y squared minus y, and we will graph it. Yeah, it's unstable. So it does make sense for it to go off to infinity. I just did not expect it to go that fast. Pulling up our Excel spreadsheet again. Let's say that we have a starting y value of negative 2. Well, negative 2, it says that our end behavior is 0, which makes sense because 0 was stable. And if you look at this, as it goes, it gets closer and closer and closer to that value. Still just don't feel comfortable with these formulas. I feel like there's something that is off here and I am not seeing what it is, because that seems to go to 0 very, very quickly. And I don't think it should go quite that quickly. But again, that's that I could be surprised, and that maybe that is the case. We could then say that what happens if we start at 0.5? Again, 0 is stable, and so I would expect this to go to 0. And sure enough, this does go to 0. And again, it goes there fairly quickly, it seems. Well, no, I guess that seems reasonable. It's a fairly slow rate. And maybe that's reflected in this graph. So looking at this graph, you can see that starting at 0.5, it's going at a slower rate. Whereas if you are starting at a negative value, it looks like it's coming up here to 0 very, very quickly. And so maybe if we started at like negative 100, it would still go to 0, but it might take a while for it to get there. And so let's try that. If we started at negative 100, oh, that's very interesting. It looks like at some point there must have been some computational error. Yeah, I'll have to play with this Excel spreadsheet and see what's going on there, because there's definitely something which is not quite right with it. I'm not 100% sure what it is. But I will let you guys play with the Excel spreadsheet to see if you can figure out good old Euler's method. It could be that my Excel skills are not as good as they once were. But with that, we'll come to the end of today's lecture. And so thinking about what we did today and what our goal was for today, it was primarily to introduce the idea of differential equations. And so we wanted to introduce how you can model using differential equations, as well as just the basic terminology and what phase diagrams are and what they represent. And I feel like we got away with that pretty well. When we were thinking about all of the stuff that we were doing, we tried to bring it back to these graphs. Let me bring that graph back up. Our phase diagrams, our direction fields. And we can model differential equations using direction fields. It shows the direction that a differential equation is going to be going in at a particular time. We had the three different types: the pure time, the autonomous, and the non-autonomous differential equations. We also talked very briefly about the idea of ordinary versus partial differential equations. But most of our time was spent dealing with autonomous differential equations and trying to understand how to calculate equilibrium. We then did Euler's method, and we did it kind of poorly. Sorry about that. But it's a way of approximating differential equations. And as we saw, it's not a very good tool for approximating differential equations. Even if you're using extremely small delta values, or delta x or delta t values, you will take it'll use a lot of computer power and you still won't get that accurate. 10,000 intervals, you'll still be off by 100 or so. And so that's kind of an issue with Euler's method. But that brings us to the end of today. We only have one more video to go, and that's going to be covering section 7.4 through 7.6. And that'll focus primarily on the idea of two-dimensional flows instead of one-dimensional flow. And so instead of dealing with single variable differential equations, we'll be dealing with systems of differential equations which have two interacting populations. See you then.